Okay, thank you. Thanks for the invitation to speak here. Yeah, I'm going to be talking about scattering strings of quantum extremal surfaces. This will be based off some work that came out this summer with Ben and Tom Faulkner. Ben is here. And then I'll also touch on some upcoming work with Ben, which hopefully will be out soon. Okay. So some comments. We've heard just from Arvin, and we've heard a lot in the last few years about how this quantum extremal surface prescription from Aaron and Netta has given us a lot of insight into the interior of black holes and black hole evaporation. And so I think it would behoove us as a community to understand how general this prescription really is, what happens in more general theories of gravity, for example, what happens in string theory. So a question that I wanted to ask today is there still a useful notion of a quantum extremal surface in a bulk theory where stringy effects are important? Okay, this is, I'm not going to have a definitive answer to this question, but that was sort of the motivating question. And the way I'm going to try to answer this question or probe this question is that I want to calculate a boundary quantity which senses in some way the position of some bulk quantum extremal surface. And then I can compute that boundary quantity in a more general setting and try and interpret, read the tea leaves, so to speak, of what's going on in the bulk. So with that said, here's the setup of this talk, and it's just going to be basically this setup the whole time. So let me go through it slowly so everybody understands what's going on. I'm going to consider this setup that was introduced by these authors, Almeri, Mahajan, and Avicena, where we had, they discussed a situation where you have ADS2 JT gravity coupled to some matter. So you have an ADS2 black hole. And the matter is, let's say it's some theory. In my case, in our case, we'll consider a 1 + 1 CFT. And the matter can propagate freely through the boundaries and into these non-gravitating bads, okay? These bads are just flat space. The picture here is that this is some sort of semi-classical description of some dual picture where you have this is a time slice of the dual picture. You have some bath L and some right bath R, capital R. And the bads are coupled to some 0 + 1 dimensional quantum systems, which are assumed to be holographic, for example, maybe like the SYK model, something of that sort. And you consider a thermally entangled state. You consider the thermal field double. So that's the boundary picture, so to speak. And you consider, and so in this paper, what we considered is basically the setup of Hayden and Preskill. So what we want to do is insert some operator, insert some particle near the boundary, and let it fall into the bulk. And what we're going to try and do today is compute some quantity which senses when this particle goes from the entanglement wedge of one region into the other. So the entanglement wedge that we're going to consider is going to be associated to a region which is the whole left, union this left quantum system, plus some interval in the right bath. The interval I'm going to call I, and the remainder of the right bath I'm going to call little r. So little r is the complement of L and I. Okay, so that's the idea here.
So the little I also include the right system, you know, the right SYK.
Little I does not include the right SYK. Little r includes the right SYK. Yeah. So yeah. So what am I going to do? I'm going to consider a state with some excitation. I'm going to act on the state with some unitary. The unitary is going to look like 1 + I times some small number lambda times some permission operator phi. Let's say phi is dual to some bulk particle, or it's one of the operators in the CFT. And this, as I've written it, is not quite a unitary, because to make this state well defined, I want to evolve this excitation into Euclidean time a little bit. This suppresses high energy excitations and makes the norm of the state finite. So this is not quite unitary, but for small delta, I can think of this as basically being close to a unitary, because I can trade off this small amount of Euclidean time evolution for a small amount of Lorentzian time evolution. So this is you should really think of this as being close to a unitary. And this delta parameter here, I'm going to think of as as sort of a smearing scale, okay? So I'm smearing the operator on times of order delta. Now, when does this transition happen? Well, Hayden and Preskill taught us that this transition needs to happen when this operator has fully scrambled. Basically, it needs to be back in time from the region relative to the region by a scrambling time. And you can do an explicit calculation in the bulk, and you find the position of this quantum extremal surface, and you find that this particle transitions from one entanglement wedge to the other precisely at a scrambling time. Okay. So that's a quantitative way of realizing the Hayden and Preskill protocol. And so given that, and given the fact that we expect in general that a maximally chaotic theory or a sub-maximally chaotic theory is dual to a theory with non-zero string length, a different way of asking the question I asked at the beginning would be, is there still a useful notion of a quantum extremal surface in the bulk dual for a boundary theory which is sub-maximally chaotic? So what are the effects of sub-maximal chaos on this quantum extremal surface prescription? Okay. One other way of thinking about this question that I just wanted to sort of advertise quickly, which is sort of the way I like to think about it, is when you have this boundary region L union I, you can think about something called its modular flow in the thermal field double state. So this delta operator is what I'm going to call the modular operator, but it's really just the density matrix for the region. So if you have some region A, it's this density matrix for A, tensor the inverse of the density matrix for the complementary region. And the expectation due to work by Jafferis, Lukowitz, Navasena, and Su is that if you act with this boundary modular flow, the bulk dual of that should be modular flow in the corresponding entanglement wedge of that boundary. Now, in general, when these states are very complicated, this flow could be very complicated. But what we expect is that for observables near the quantum extremal surface, this flow is approximately a boost, okay? So here I've pictured, this is the example from before, I've imagined that the quantum extremal surface is sort of null separated from the bifurcation surface, that's this black dot. The red dot is the quantum extremal surface. And so what you can do if you have control on the boundary over this modular flow is in the bulk, you can do a boost once about the bifurcation surface, and then once about the quantum extremal surface. And because of this SL2R algebra near the horizon, you approximately get a null translation. That's interesting because this null translation you can use to say move operators behind the horizon. You can do interesting things with it. This is, these operators were constructed in JT gravity by these authors here. And this is also sort of related to this recent work, this interesting recent work by Leuthauser and Liu, where they tried to construct similar generators that move you behind the horizon. Okay, so given this, yet another way of asking the question I'm interested in is what happens to this SL2R near horizon symmetry when you include stringy effects? Okay. Because the fact that the theory was maximally chaotic led to this approximate, we know from this work by Lin, Navasena, and Zhao that this approximate SL2R symmetry is related to maximal chaos. Okay. All right. So how am I going to do this? How am I going to what boundary quantity am I going to compute that senses the position of the entanglement wedge? So the quantity that I'm going to talk about today is the so-called relative entropy. Relative entropy is a measure of distinguishability of two quantum states. It has this formula in terms of density matrices. So for some subregions, say the little r region, the relative entropy is the difference of minus the von Neumann entropy plus this expectation value of this modular Hamiltonian in the rho state. Here, rho I'm imagining is my excited state that I talked about earlier. It's the state with the particle. And sigma is the thermal field dot. These are the density matrices reduced to the little r region. Some facts that will be important for intuition are that the relative entropy is always positive, and that it's equal if and only if the density matrices agree on little r, okay? So this means these are why it's a good way of distinguishing two quantum states. So now let's go back to the setup. So what happens when I drop the particle in at early times? Well, on the t=0 slice, the particle is basically in this entanglement wedge, which is associated to little r union the quantum system. So what we expect is that the relative entropy between these two states is large on little r, and it's approximately 0 on Li. This is because we're acting basically with the unitary, and so that means that when this particle is well localized to the entanglement wedge of little r, that means that the density matrices on Li are approximately equal, because they just differ by a unitary action on the complement. Okay? But when this particle transitions into the entanglement wedge of Li, what happens? Well, the opposite happens. So now the relative entropy is approximately 0 on little r, and it's large and positive on Li. Okay? So that actually inspires us to compute a slightly simpler quantity, although at first glance it doesn't look simpler, which is the difference of these two relative entropes. The reason this is simpler is because these relative entropes had von Neumann entropies in them for the state rho. But when the state rho is pure, if I subtract the relative entropy for a region minus its from its complement region, the von Neumann entropy on two complementary regions is the same, and they cancel out, and you just end up getting the expectation value of some linear operator in your state psi. Okay? This operator depends on some reference state, but it's linear in the sense that it's just an expectation value of some operator in state psi. And this operator ends up being log of this modular operator for the thermofield double on the Li region. Okay, so again, I said this thing we think in gravity approximately generates boosts about the quantum extremal surface. So this is really the energy, the boost energy about the quantum extremal surface. We're used to maybe the energy, the boost energy of a state about the bifurcation surface. This is about a shifted surface. Okay, so with that in mind, what do we expect in gravity for this answer? So using this SL2R symmetry that I described earlier, in gravity, we expect that this generalized boost energy is just the boost energy of the about the bifurcation surface of your state, plus some expectation value of this null energy. Okay. So what is this? Well, you can do a computation, and as you're boosting the particle back in time, the insertion back in time on the boundary, time evolution on the boundary is related to boosts about the bifurcation surface. So this boost energy doesn't change, right? It just meets with time evolution, so it doesn't change. But this null energy grows exponentially in time. This is just the same story that we're familiar with in these chaos discussions. So the answer you get is 1 minus some small piece times a piece that's exponentially growing in time as I move time more and more negative. And when this crosses from positive to negative, remember this is this difference of the relative entropies. When this crosses from positive to negative is precisely when this particle is null separated from the entanglement wedge, boundary, from the quantum extremal surface. Okay? So this is what we expect in gravity. This is an explicit bulk calculation. How about on the boundary? Okay, so on the boundary, the issue is that this region, L union I, in general has some very complicated modular operator. The density matrix on rho, the density matrix on Li is not just some simple expression. So in general, we don't have much control over it. But in this paper, we took a simplifying limit, which was that we can take this region here, I, very small. When I is 0, we just have L, and L is a simple, its modular operator, or its density matrix is just the normal time evolution operator. So this is, in some sense, close to an easy to understand density matrix in this small I limit. And in that limit, what do we find? Well, when I is very small, you expect that the state on L and I is close to being factorized. So it's approximately the rho L times the rho I state, plus some correction, which you would expect comes from the operators in the state, in the theory, that have the largest correlation between L and I. The operators that have the largest correlation are usually the lightest operators. Their correlations die the slowest between these two states. And indeed, by explicit calculation, that's exactly what you find. What you find is that to leading order in the size of this interval, the difference between the modular energy in the Li region and the L region is just this bilokal operator. There's some kernel, you integrate against some modular time in the thermal field double, there's some kernel, blah, blah, blah. It doesn't, the details don't matter for this talk. But the point is that this is small. So the correction is subleading in the size of I, okay? And the point is that this thing is bilocal, interestingly. So this thing looks like an operator on the left times an operator on the right, integrated against some kernel. Okay. So now we want to compute the expectation value of this quantity on the boundary. I'm going to forget about all the smearing and all that stuff. It's not important. Just think of this as some bilocal operator. And now when I go to compute on the boundary this generalized boost energy, I get a contribution from the boost energy about the bifurcation surface, plus some contribution, which to leading order in this small parameter lambda, which was sort of turning on a source for this operator, is just this 4-point function. Okay? It's the expectation value of this O left OI operator in this excited state. This is an out of time ordered correlator of the type that's been studied by many authors in the past. And there's a standard way of computing this thing. The way of computing is to map it to a scattering experiment in the bulk. And that large TR, remember, for the transition to happen, we knew that that TR needed to be a quarter of the scrambling time. So for large TR, you can use this iconal approximation. So let me be clear, this is sometimes a bit confusing. I'm doing a boundary calculation. In this step, I'm moving into the bulk to compute this boundary quantity, okay? And this scattering experiment looks like there's an excitation from the phi particle, and it has some momentum wave function, and there's an excitation from the O particle, and it has some momentum wave function. And they scatter with some scattering phase, which is approximately just a phase in this iconal.
So here the O and OI are choosing in a symmetric location, such that it's true.
Yes, so actually what ends up happening is that they are symmetric.
Yeah, I think for example, in that reference, they just choose like a dual operator from them. Here you are doing it the same way.
It ends up being very similar to that. Yeah.
Or in other words, let me ask, like, could you choose different location with
you could.
And would that?
It wouldn't change the answer much, but yes. Okay, and so now I just have some integrals that I need to do to compute this thing, and I need to tell you about the scattering phase here. And this is a standard story. This is not any of my own work. I'm just reviewing work here, other authors, namely these authors. So when you have a theory with gravity in the bulk, this phase here is just a simple linear function of the center of mass energy, P plus times Q minus, times G. Okay. The expectation in higher dimensions, this model I'm working with is a toy model on 1 plus 1b. The expectation in higher dimensions is that in some sense, this gets raised to a non-integer power, okay, some fractional power, which I'm gonna call my stringy exponent, or my stringy scattering phase. Here I'm following the work of Nadasen and Sanford Yang, who used this sort of as a 2D toy model of the higher dimensional case. We can also do these calculations and did it in the paper in higher dimensions explicitly, and it does not change the answer qualitatively. But the idea that you should have in mind is that this J exponent here is approximately 2 minus some correction, which is of order the string scale over the ADS scale. Okay. And the reason I'm using J here, J equals 2 is the spin of the graviton. So it's the spin of the particle that these two particles exchange in their scattering. And in string theory, you have to sum up a whole number of higher spin particles, and this is called regularization. And the effect of summing up all these intermediate particles is to shift this exponent down. Okay. So what do we get? So now we can do those P plus and Q minus integrals. We can compute this, and what we get is that when J is 2, when you're in a theory of gravity, you get exactly the answer that you wanted to get from gravity. You get an answer that goes from positive to negative, or in this case, negative to positive. Overall sign doesn't matter. When the quantum extremal surface when the insertion is null separated from the quantum extremal surface, this delta XQ comes out of the boundary calculation. and it agrees with the bulk calculation. Okay, but what happens when j is less than 2, so when stringy effects are important? Well, what happens is that this exponent here gets shifted. That's this fact on the boundary that the Lyapunov exponent is sub-maximal. So your j minus 1 is less than 1. But you also, this coefficient here gets modified in interesting ways. So first of all, you pick up some dependence on the smearing scale. So this delta that was the smearing scale of the insertion shows up. And also this delta x here depends now on the mass or the dimension of the particle that you are throwing in. So before delta O shows up in here, I suppress that dependence, and now this delta x depends on both delta O and delta phi. So the transition time, the time at which this thing goes from being positive to negative, seems very much probe dependent. Depends on details of exactly what you're throwing in and how you prepare the state. Okay. So this crossover time, this transition time is dependent on probe properties. So what's going on? We don't know, but let me offer one bulk interpretation, which was first suggested to us by Douglas Sanford, which I am partial to, although I'm not sure it's totally right. I'll explain why. So we have this formula. So what's going on? This formula, because j minus 1 is less than 1, the turnover time, the transition time is much, you need to bring the particle down earlier to get it into the entanglement wedge. But the fact that this turnover time is so dependent on the probe suggests, well, maybe maybe what we're seeing here is not really a property of the quantum extremal surface itself, but more a property of the probe that we're throwing. So the idea is that maybe as you throw this probe in, it spreads out in the longitude in this x plus direction. Okay, it spreads, and it has some length, and that's why to get all of it in, you need to send the particle back. You send it in early, right? And if you just take that interpretation seriously and say, well, let's assume that the quantum extremal surface hasn't moved, we can use this expression to estimate the size of the longitudinal spread of this x plus spread. And for j close to 2, for small string length, you get some answer like this. So the delta x plus spread of the probe that you threw in is proportional to the string length. There's this factor e to the 2 pi tr times a log. Okay. The appearance of this log is reminiscent of previous discussions of longitudinal string spreading by Susskind and Dodelson and Silverstein and others. But this expression is actually different. It doesn't agree with those expressions. In particular, in previous works on longitudinal string spreading, what happened was as you threw the string in earlier and earlier, the length contraction and the spreading effect actually canceled each other. The string just stops changing in size. Here, however, because this is an e to the 2 pi tr times a log, the length contraction here, this is the length contraction effect, actually wins out. So you can still fit the string into the quantum extremal surface. You still get a transition, it's just at an earlier time. We dug around and there were actually some papers that from back in the day that predicted an answer similar to this, but I'm not sure how much to trust those answers. So given that this is in conflict with much more probably trustworthy calculations on the string spreading effect, we're not totally settled on.
So can you second why I will exponential 2 pi tr term in delta?
Sorry, say that again.
Can you say again why you have exponential term in the delta x plus?
So what I've done here is I've just taken the turnover time from this. So when this goes to 0, I've solved for e to the 2 pi tr. And then I've subtracted off from that answer the position of the quantum extremal surface in gravity. and then I took the j close to 2 limit, and I expanded out. And you get, when you do that, you get an answer which has some e to the 2 pi tr. But sorry, maybe what you're asking is, the interpretation of this is a length contraction. This looks like an object which is length contracting as you're moving it back in time, and spreading sort of in its own frame.
Oh, that makes sense.
Okay, I'm going to transition now into this upcoming work with Ben, where we tried to do similar calculations in the SYK model. So you could try and play a similar game in the SYK model, although it's not obvious at first glance that it would work. So here I have 2 SYK models, and they're thermally entangled. These dots are my SYK fermions, and they're all, experiencing all-to-all interaction. I'm going to assume for the rest of the talk that everyone here is relatively familiar with the SYK model. I apologize if you're not. You can do a similar thing. You can take some subset of fermions in one of the SYK models, say the right one, call it K fermions, and you can union those with all the left. And you can ask, if I insert a fermion, say here, at some time, at what time is that fermion, say this blue fermion, accessible from the left union this small number of fermions? And to make analytic progress, I'm going to assume that the total number of fermions in each system is much bigger than the number that I pick out here, but that this number is much bigger. Okay. And now we wanted to compute this modular energy, and it has log of some operator in it, and we've learned we know how to do that just using a replica trick. And if you write down what this replica trick is, you can actually solve for this correlation function at large n and also at large q using the G sigma action. Okay. And what we do is we solve the G sigma equations perturbatively in k over n, and this amounts to solving them with some funny boundary conditions. Computing this amounts to solving with some funny boundary conditions for the k fermions versus the remaining n minus k fermions. And the answer you get is in terms of the OTOC, the out-of-timer correlator, which is not a surprise. And at large Q, we can utilize this work of Alex Strecker to compute the answer. And what we find is the following. We find that the generalized boost energy for L and K is just like the gravity answer. This is boost energy about the bifurcation surface times this quantity. And so this gives us a prediction for a quantum extremal surface associated to a subset of spins in SYK. It predicts precisely this answer for delta x for the position of the quantum. You can try and check that. This is a prediction. You can try and check that prediction in some bulk model. And here's the model that we tested. Imagine that in the bulk you have n fermions, n massive fermions. They have some mass set by their boundary dimension in the large beta J limit. And there are n flavors in the bulk. I'm going to separate out k flavors. I'm going to call them the red flavors, and then the black flavors, then the remaining n minus k. And for these k flavors, there's some small, I'm going to imagine that there's some small quantum extremal surface or small entanglement wedge, a quantum extremal surface very out near the boundary that's associated to those k guys. The intuition here being that if you have one of these k fermions, as soon as you time evolve, as soon as you get one commutator basically with the Hamiltonian, that fermion leaves because you have way more complementary fermions. That fermion just leaves that algebra of fermions. So the distance of this entanglement wedge in the bulk should be order 1 over beta J, the coefficient in front of this Hamiltonian roughly. And then with that fixed, you can try and find a quantum extremal surface for the remaining guys, where the entanglement in the fields is only between these k guys, and we don't include the We include a bulk entropy term from the n minus k, but there's no entanglement between the n minus k fermions, the black fermions, and the near boundary control. And you can do this calculation. It's actually very similar to the calculation I did earlier because you assume that this region is very small, so you can work perturbatively in the size of that region. And you get an answer that agrees even up to order 1 coefficients with this prediction. This is kind of a strange bulk picture. There are, weird aspects to it. So I'm not claiming that this is always the bulk picture, but it seems to give the right answer even up to order 1 coefficients in this case. Okay, that's basically all I had to say. I just to advertise the paper. One thing I didn't want to include because it's technical and I didn't have much time was you can compute. We computed today this full modular energy or this generalized boost energy. That's one quantity that senses the transition, but there are other things. Actually, that's not a very rigorous way of sensing the position of the quantum extremal surface. What you really want to know is when is this particle reconstructible from one region versus the other. And so to figure that out, you need to compute some slightly different quantities, which we do in this paper, and it relies on us computing what's called modular float correlation function. And it's a bit gory, but we were able to do it. And the answer that you get is qualitatively, well, you can get more data about how this transition happens. And what we find is that in gravity, there's a sharp distinction between the particle being inside and outside the entanglement wedge. And when this Lyapunov exponent is sub-maximal, the distinction fuzzes out. Okay, that's it. I have some open questions here. One thing I'd be interested in discussing with people is I've always felt that there should be a connection. Yeah, there should be a connection between the story of the quantum extremal surface in SYK and maybe ideas about operator size. Something along the lines of when the operator grows too large, you need to reconstruct it using a different region, something along these lines. I haven't been able to make that precise, but I'd love to talk to people about that. And one dream of this stuff is that if we have a quantum extremal surface in SYK, we could use it to construct these generators in a well-defined boundary way that could allow you to maybe move operators into the interior. And I was curious how far you can push this before it breaks. Can we get to start seeing effects like from the singularity or from the inner horizon? And of course, we need to understand this bulk picture a bit better about string spread. That's all. Thanks.
You also include the effects of changing the wave function? This gathering.
In the toy model at the beginning, no. In SYK, well, we're doing kind of calculations. So, yeah, it would be interesting. Yeah, right. It'd be interesting to understand the. So you pointed out that in SYK, the wave function changes in a nice way that interplays with the different pattern phase. It would be interesting to see how that changes some of the formulae we have.
Has it changed? I thought in SYK, the wave function does not change.
As you move away from large beta J, well. That's finite beta.
Oh, it means the dependence on beta J?
It's because the conformal answer is no longer. Yeah, we're talking about away from beta J.
But in your computation, you didn't use different.
No, oh, sorry, I forgot to point out. In this formula for the, this is related to this fact. In this formula for the modular energy in SYK, the delta dependence in this coefficient is gone even for finite beta J. It was interesting that it was delta dependent, and I think the reason that the delta dependence disappears, I need to check this, is exactly this effect that Henry mentioned, that the wave functions in the scattering experiment change.
I have a question. So maybe I missed something. So here the delta x does not have the exponential pattern piece, right? The phrase is the delta x, but in your previous bulk gravitational computation, you have a delta x equal to something like a log, something like the size of the delta.
So if I take this expression at finite beta j, and I want to read off when this hits 0, and then I expand near at large beta j, I will get a log term in this string spreading calculation. I'll get an answer just like this, except this delta dependence will become.
Oh, okay.
Yes.
No, let's try that again for this one.